So ELBO equivalence. So as I said, whatever we have seen so far is all that is there to the training, but there are, as I said, multiple ways of representing this same thing equivalently. So we will see how to do this. Okay. So recall that the denoising matching term or the consistency term that we had was 2 sigma q squared times mu theta of mu theta was a function of xt minus mu q, and this mu q was a function of xt and x naught. I have been omitting this term to make it look simple, but this is what it is. Now what is mu q? We know that mu q of xt comma x naught is given by 1 minus alpha bar t minus 1 times root of alpha t divided by 1 minus alpha t bar times, so this is the constant that gets multiplied with xt, plus 1 minus alpha t into root of alpha t minus 1 bar divided by 1 minus alpha t bar this times x naught. So mu q was a linear combination of xt and x bar, as we saw, right. Now we have mu theta. Okay, so the mu theta takes xt. So what we can do right now is that we can actually express mu theta also in terms of xt and something that we estimate. So how do we do that? We will just copy this particular term here and this constant as well. But instead of x naught that comes up here, I will write that as x theta at xt, okay, where x theta of xt is the output of the neural network. This point is actually often confused. Okay, so how did this come from? It's pretty simple. So what we have done here is, remember that mu theta that we have, which comes up in the ELBO, is something that we design. Okay, so we can design it the way we want. So what did we do here is, since mu q, which is the, okay, so now the loss function here, right, is a regression over mu q. So mu q is fixed. You can look into mu q as the true value upon which you are regressing, and mu theta is the output of the neural network, right. Now if the true value that we are regressing can be represented in terms of xt and x naught, then the output of the neural network which we are using to regress can also be represented in terms of xt, okay, the same term that is in mu q and something that we are learning. So why would this work? This works because mu theta, right, is a vector in d dimensions, and we know that we can always reparameterize a Gaussian distribution using constants. Now suppose without this reparameterization our neural network was giving some mu theta as an output. Okay, we can always adjust the output of this neural network with some scale and shift such that this mu theta takes the particular form that we have. Does that make sense? So I will just simply repeat what I just said, because this is something that is often confused. So basically what we are saying is, so mu q, so mu q look like some constant c1 times xt plus c2 times x naught. So this is how it was looking. So what did we do is, we wrote mu theta also as c1 times xt. So note that this xt C1 times xt is a constant, okay, given a particular xt, given a particular time instant t, C1 times xt is a constant. I can write my mu theta as C1 times xt plus C2 times some x theta. Now what I am saying is, I can always adjust my x theta, which is the output of this neural network, such that my mu q can be represented in terms of C1 times xt plus C2 times whatever that x theta is, because it is only a scaling and linear shifting. Okay, so this is nothing but the classical reparameterization that we are doing. So since we are designing how our mu theta should look like, I can write down my mu theta in terms of something that closely matches mu q, but I still have something that that is to be optimized, or rather predicted using the neural network. So why did I do this? This is simply done in practice to make the interpretation of DDPM prediction a little more interpretable, a little more tangible. So with this, what happens is, with this our loss function, which is 1 by 2 sigma q squared times mu theta minus mu q squared, this will have the following form. So this will be 1 by 2 sigma q squared times, I will simplify all the constants and just write them. So mu theta is written in terms of alphas and xt and x theta. So this is 1 minus alpha t bar see if I am correct, 1 minus alpha times root of alpha t minus 1 bar, this into x theta of xt, which is the prediction of the neural network, minus x naught. Okay, so all these are I can rearrange the other terms and simply write this as 1 by 2 sigma q squared into 1 minus alpha t squared to alpha t minus 1 bar divided by 1 minus alpha t bar squared times theta at xt minus x naught. Okay, so this is the consistency term. So this has a much more interpretable form in the sense that, so why is this interpretable? Now previously we were saying that this is a regression on mu theta. So now with this formulation we have a different interpretation. As I said, mathematically speaking they are exactly equivalent and nothing changes implementation wise, but for what is that we are estimating, okay, how do we want to interpret it, but interpretation wise this looks much better. So now this takes xt as an input. Now this term is now x theta, x cap theta, and this is a regressor on x naught. This is a regressor on x naught, because what is the loss function here? Loss function is simply regressing upon x naught, a regressor on x naught. Why is this important? As I said, this is a question of interpretability. With this particular type of interpretation, this can be the above network can be viewed as a denoiser. Denoiser for the data point x naught. Yeah. This is the major advantage of why one should reparameterize mu q and mu theta in terms of xt and x naught. This is because this entire network, the neural network that is now being trained, which is a regressor on X0, can be visualized as a denoising network or a denoiser for the given data point X0 at all noisy instances xt. So, now what is this doing? Recall what is our xt? Our xt is the tth latent space, and in the particular construction of the forward process for the DDPM, the forward process can be looked into the process of noisifying the image. So, now we take a particular data point x0 or an image x0 and we keep adding noise as we saw to get an xt. Now, xt is that version of the data which has been noised, okay, and what we are trying to predict from it, we are trying to predict what the input image was that led to this particular noisy image xt, right. So, in that sense, this entire neural network that we are training can be looked into as a denoising network on the data distribution, okay. So, that is one of the reasons why this thing is called, denoising diffusion, a denoising diffusion probabilistic model. So, what we are actually, there are two reasons why we call it denoising diffusion models. One, the data generation can be, or the reverse process or the backward or the decoding process can be looked into as the denoising process. The other reason is that the neural network that we are training can be interpreted in terms of denoising a given data point, okay, at some noise scale or time scale, okay. Now, one other thing that is to be noted here is, which is very, very critical, is unlike the neural networks that unlike the generative models that we saw so far, which are the generative adversarial networks and the variational autoencoders, the neural network that we are training does not give us the samples from the distribution that we are seeking, okay. So, this is not sampling. So, let me just write that down. So, unlike in a GAN or a BAE, the neural network that gets trained in DDPM, neural network that gets trained in a DDPM does not output the novel data point, okay, right, even after training. So, this is true even after training. So, the neural network is not giving you the output of the generated sample. So, how do we do that? We will see that in a while. How does one do inference in a DDPM? We will see this in a while. We will see that in a while. But this is something that is to be noted, is that the neural network that we train in the context of a DDPM is not a sampler, okay. It is simply a regressor over the noisy sample. It is simply a regressor over the input data point xt. It is not, let me write that down. So, this is a regressor on the input data point. So, regressor on the input data point xt. Input data point x0, not xt, x0. So, this is a regressor on the input data point x0. So, a GAN, right, post training, all you need to do is sample a point from the normal distribution, give it to the generator and gives you a point from the distribution of interest. And in a VIE, same thing happens with the decoder. Here, the neural network that is being trained will not give us the novel data point from the distribution that we are modeling, okay, novel data point from Px0. So, with the distribution that we are modeling, Px0, which is the true data distribution. Okay, then the question is, how do we sample from a DDPM? We will see that in a while. True data distribution. Okay, so this is one thing that is to be noted. Now we know everything. Now we have everything that we need to train a DDPM. So let me write the training procedure now. How to train a DDPM given a particular data set.